Everybody is actually on the same page. So the problem was, all right, I don't have the problem here on this computer, and I don't think I can, all right, let me see. So the problem was we have this buck topology which is being controlled by a peak current mode controller. And we are not even using any external or auxiliary ramp, so very, very simple. And the reference for the current is 4.416 amperes, and the load is 5 ohms, and the duty cycle is 40%, and then the output voltage is 19.2 volts. And so these pieces of information are provided. Now, the question is, what should we adjust our IREF at so that the output voltage would be 14.4 volts and the load hasn't changed, but the duty cycle has changed from 40% to 30%? I don't think I can write on this PDF. I'm assuming that I cannot. Oh, actually, maybe I can. Let me see. No, I can't. So I have the solution. Let me open the solution one. So a lot of you guys assume that IREF and IL are the same. Now that assumption is used when you're trying to develop a small signal model, an approximate small signal model. When details of numbers are provided that IREF is this much and Vout is this much and load resistance is this much, you have to be careful about the assumptions that you make. So IREF is a flat line of 4.416 amperes. And, okay, before we get there, let me return it to you guys. So as you can see, output voltage is given and the load resistance is given. And remember, in the buck topology, the output voltage divided by the resistance would be the average value of the inductor current, right? So we pretty much have the average value of the signal as well, which is this dotted line over here, which is 19.2 over 5. All right? So, and the distance between this dotted line and the reference is half of the peak-to-peak ripple in the inductor current, which is delta IL over 2. So this equation that I have down here is the average value of the inductor current is the reference for the current minus half of the ripple, okay? And for half of the ripple, you can either relate it to the mode 1, which is V in minus V out over L times D times T, or in this case, I'm relating it to the second mode, which is V out over L times 1 minus D times T. And there is a division by 2, obviously. So if you look at this equation, we pretty much have all the parameters except the switching period and the value of the inductor. So once you plug in all the numbers, you end up with T over L is 0.1. All right. So so this is like the sentence that all the information was provided, and we kind of do almost the same thing for the new numbers, which is the output of 14.4 volts and a load resistance of 5 ohms and a duty cycle of 30%. So technically now I have a numerical value for T over L, which is 0.1. Now I plug in the new V out and the new duty cycle to find IREF, and IREF turns out to be has to be set as 8 volts or amperes. That doesn't matter. These signals are all in voltage, but you interpret them as a current anyway. So as it turns out, and we have actually mentioned this before, if you are doing peak current mode control, you are not really directly controlling the peak. You're not really directly controlling the average value of the signal. You're only controlling the peak value of the signal. So there is a bit of an error or offset between your reference and actually what you're feeding to your load in terms of current. So this is called peak to average error, basically. So there are actually papers looking into this error, trying to, I don't know, come up with some ideas or approaches to eliminate this error, which is ultimately an average current mode controller, something like that. Any questions? Yes.
So is it not correct to just find out the ripple because the inductor controls it, and just, I mean, because the inductor remains as it is and the switching frequency remains as it is?
Okay, but ripple changes. So remember, your ripple is this expression over here. So your ripple is dependent on the value of your duty cycle. So if you change your duty cycle, your ripple changes. It also is dependent on your output voltage. So you cannot assume that your ripple is constant. It's not constant. Any other questions? Okay, so this was quiz number 4. We had one on-campus and one off-campus student who actually got it totally correct. All right, so we are going to continue our discussion on power factor correctors. So what we did last time was, let me see. We decided that the boost topology is a good candidate to do power factor correction, and then we started looking at different ways of doing power factor correction. So the very first method was operate the converter under discontinuous conduction mode and then keep the on time of the switch constant. Very, very simple, because you don't even need to measure the current. Basically, you just keep the on time constant. And we looked at some math, and there's a paper involved, and we realized that basically, depending on alpha, which is the ratio between your output voltage and the peak value of your input voltage, you can achieve certain, power factor. Like in our simulation, I think it was like 70%. Then the main problem over here is that we are operating at discontinuous conduction mode. So discontinuous conduction mode, because the fluctuations in the current is too much, the RMS value of the current is too high. So that means the RMS value is too high as opposed to delivering a small amount of power to your load. So one alternative approach would be, we still want to be, obviously, ideally you want your current to be continuous. So one approach would be to eliminate this kind of a dead time over here, that we are not really getting any power from anything, okay? Your inductor is almost off, it's not even energized, and all that is happening is your output capacitor is being discharged by the load. So an alternative approach would be doing that, which is like a critical conduction mode, meaning that you turn the switch on and then wait for T on to pass by, and then you turn the switch off and watch the current. As soon as the current gets back to 0 or tends to get really close to 0, you start the next cycle and just keep repeating that. I didn't have a simulation model for this, but as it turns out, it's almost the same thing. You can improve your power factor. You can achieve like 70 or 80% of power factor. The other alternative is going to the continuous conduction mode. In other words, force the current of the inductor to follow a particular pattern using current mode control technique, for instance, peak current mode control technique, and that pattern is basically proportional with the input voltage. So this would be the overall diagram. You have your AC source, you rectify it using a bridge of diodes, and then you have this boost topology. And at the same time, remember, you're also trying to regulate the output voltage. So I have a voltage loop and a current loop and a feed-forward loop, basically. So in this loop, what's happening is we are measuring the output voltage, comparing it against a particular reference, and try to regulate the output voltage at that reference. We have a compensation network, and the output of this compensation network is almost we are going to see that in simulations, almost a flat line, which is determining like how much power we need on the output side. And then this signal is being multiplied by a signal that we obtain by scaling down our input voltage, something that is basically proportional with the input voltage. So then you have a signal like this. And then beyond this point, it is just, for instance, a peak current mode controller. You're forcing the inductor current to follow this pattern. That means you have to measure the inductor current. There is an external ramp involved. At the beginning of the cycle, you turn the switch on. When the inductor current tends to get larger than the reference, you turn the switch off, and I mean the whole classic peak current mode control. So we discussed this a little bit, and now we are trying to kind of look at some simulations, okay? And the model is already on Blackboard. All right, let me see. Okay. So the model is here. What you see on the screen right now is just I'm using Simulink. There is no switch or diode or anything. It's just the math that is operating. This is just a power stage. You have the input voltage of 110 volts RMS with 60 hertz of frequency. Then you kind of rectify that, just get the absolute value of your signal. Your inductor is relatively large, 360 micro, and I have some equations talking about this inductor. And the output resistance is 20 ohms, and the output is supposed to be regulated at, I think, 200. So remember, in these boost PFC converters, your output voltage is all the time larger than the peak value of your input voltage. So 110 volts RMS gives you a peak of about 155, I believe. So my output is 200, which is larger than that. So I think I have already run this. So just let's take a look at some of the results. Okay. So on the top trace, the kind of red one is the output voltage. It is 200, which is where it is supposed to be. If you zoom in, you are going to identify a relatively large ripple, almost like 8 or maybe 7 volts peak to peak. And we have talked about it before. You can really eliminate this in a very effective way. Let me see the second trace is the rectified version of the input voltage. So I'm just plotting them together to show you that my output is supposed to be larger than the peak value of the input. All right, so let's look at this one. The second trace is the inductor current. As you can see, the inductor current is relatively following the rectified sinusoidal signal. I'm going to zoom into it a little bit later. And the bottom trace is the output power, which is the output voltage. It's almost DC squared over R. 200 squared over 20 gives you 2 kilowatts. And this is actually too much for a boost converter to handle because we only have one switch, one diode, but it's a little bit of an exaggeration. There are several things that you are going to realize about this current. Let me just so this is again your inductor current, which is the yellow trace, and I have plotted something proportional with the input voltage so that in an ideal form, the red one is the ideal rectified sinusoidal signal. So you can actually visually compare them and see how close you are in achieving your ideal sinusoidal current. You're relatively close. There are some areas that you are not close, which is, first of all, when your voltage is crossing zero crossing error basically, your current is almost zero. There is a little bit of an offset over here. And that is because you're doing peak current mode control, and this is because of the external ramp, okay? So your reference is so small, when you subtract the external ramp from it, it is actually forcing your inductor current to follow a negative number, and because this is a boost and it cannot follow anything negative, it just remains at zero. So we can see that for a little while, you're actually hung up on 0. There is a little bit of an error over here. There is a little bit of an error over here, and we will talk about it, why these errors occur. And then there is a little bit of a problem. You can actually visually observe it over here, which you can actually observe some subharmonic oscillations actually in your current signal. And they also appear on the other end of the signal, which is somewhere around here. Actually, this one is actually doing quite well, but sometimes it happens. It actually the subharmonic oscillation problem occurs when you are getting close to 0, basically. And we are going to talk about why that is. In terms of power factor, let's take a look at our power factor. Even though our current is not exactly what we want it to be, our power factor is actually doing quite good. The filters that I have used have not settled yet, but you can see we are hovering around like 90-some%, which is quite good actually. So power factor is very good. And now let's take a look at the controller. So this is our controller. So I am measuring the output voltage. And for instance, I have a resistive divider. So it's being divided by 20. So it gives me like 10 volts. And I compare it with 10 volts. And then this is my voltage compensation network. And we're going to talk about why or how I got these transfer functions. And then we are multiplying that by a signal that is proportional with our input. And that ratio of proportionality is this weird number. If you're curious how I got this number, there's not a particular reason. I'm assuming that I am using an analog controller to implement this. And that controller is being fed by a power supply that goes from like 0 and 15 in your analog circuitry. That means none of the voltages or any of the signals within that controller should go beyond 15 or should go below 0, basically. So I looked at, okay, I want to scale down my 155 volts to something that is smaller than 15, and I just came up with this number. It doesn't, if I change this, it doesn't make a significant difference. So now my IRF is that, actually let's take a look at these two signals. So I have two signals. The yellow one is a signal that is giving the shape factor, basically. It is proportional with the input voltage. All I care about the signal is the form that it has, which is a rectified sinusoidal signal. The red one is the output of my voltage compensation network. As I said, it is almost a DC flat signal, plus obviously we have some ripple. As you can see, the peak of my signal that is proportional with the input voltage does not occur at the same time that the peak of the compensation network actually voltage occurs. So when these two signals are being multiplied by each other, there's a little bit of a distortion added to it, and that's why our current has a little bit of a distortion and error in it. The other factor to consider is we are kind of multiplying two signals. One of them is almost DC plus sinusoidal. The other one has a bunch of harmonics. When you multiply them by each other, you even create more harmonics, and you're forcing your inductor current to follow all these harmonics as well. So that's another source of distortion in your current signal. Okay, the way the peak current controller is operating is, let me zoom in. Okay, so let me zoom in an area that we don't have any significant problems. Okay, let me just further zoom in. So the blue trace is my reference for the inductor current. Then the red one is external ramp subtracted from it, and then the yellow one is the actual value of the inductor current. So I can see this is the beginning of the cycle. We turn the switch on, the inductor current rises, and it hits the external ramp, and you turn the switch off, and then it comes back down, basically. Now, when my input voltage is large, no problem. We don't have any subharmonic oscillations. However, when the input voltage is small, let me zoom in, for instance, here. Therefore, your current is supposed to be small. You can see that you have subharmonic oscillations. Here, for instance, you can see actually in one cycle, the switch is totally on. And in the next cycle, you actually make a decision to turn the switch off. So you can see that here the frequency, the switching frequency is half of what it is supposed to be because of the exact subharmonic oscillation. Or you can see here we have a period that your switch is almost on the entire time. Just at the very last, you turn the switch off, something like that. Let me try to spot somewhere that is a little bit different, or maybe a little bit uglier. Hold on. Okay, pretty much the same. You can see it's very kind of chaotic. So that was the very basic definition of our subharmonic oscillation. Question?
Is this PCM applied to rectifier?
Is what applied to?
Is the PCM peak current mode control being applied to rectifier because the output is a rectifier?
Yes, exactly. Yeah. Actually, we are using a peak current mode controller to force the inductor current, which is this yellow trace, to follow the reference, which is this blue one, with the existence of the external ramp. All right. So also, as I just talked about it a few minutes ago, when we cross 0, you can see basically what's going on in your signal. Your reference is very small. Then you subtract the external ramp from it, so you can even get to negative territory. So this is actually our 0. But the inductor current cannot get negative because of the diode, so it kind of remains at 0. So you can see that here we have an error which is called zero crossing error. If you want to eliminate this error, you got to basically get rid of the external ramp. But if you get rid of the external ramp, then you have a problem in terms of subharmonic oscillations. So let's get rid of this external ramp and see what happens. We might even get an error. Let me see. I don't know, somehow this keyboard doesn't work. Okay. It works. Let me see if I can find a constant somewhere. Okay, so I said, okay, I want to sacrifice the quality of my current waveform in terms of some harmonic oscillation, but I want to achieve a better zero, crossing error, basically, or a smaller error. Okay. So as you can see, the current is not really sitting at 0 for a little while. It's actually trying to follow the reference as much as or as close as possible, but then you can see that for a large portion of time we have this subharmonic, almost actually the entire time we have this subharmonic oscillation problem. So there is a trade-off here involved. So even as you're going down, you can see that even visually you can see this chaotic behavior over here. So the external ramp is good, but too much external ramp is not good because it adds to your zero crossing error. So there are papers trying to, solve this problem. Like one of them is to add a little bit of a DC bias to the overall signal. So you're actually rising it so that your inductor, the reference for the inductor current from which the external ramp is subtracted, touches 0. It doesn't go to negative territory. So you actually, there are papers that are suggesting to shift everything just a little bit up, like a couple of volts or something, so that this negative area in the bottom gets adjusted to 0, okay, something like that. But then the problem is, if your output power changes or the reference for the inductor current changes, this DC bias also has to change. So you have to adaptively change it, and things get really complicated. All right, so more observations. I also had, okay, here I'm actually trying to kind of highlight this zero crossing error, and I'm trying to look at the input current, the current that is actually drawn from the source on the left-hand side of the diode bridge. You can see that this zero crossing error is over there. Any questions so far? Okay, so let's talk about this compensation network. We are looking at the boost converter. So first of all, one question that you guys may have is, do we have a small signal model? Because before even designing the controller, we got to have a small signal model. The answer is yes, a lot of people have tried to do that. But the main problem is the operating point is constantly changing because the input voltage is constantly changing and the duty cycle is constantly changing. So remember, one of the first steps that we did before even developing the small signal model was to have a steady state DC analysis. But here we don't even have a steady state, or we don't have all the signals in a DC form. So that causes a problem. So some people look at the average value of the rectified version of the input voltage and consider that the DC value. So what I mean is they look at this rectified input voltage and take the average value of that and then assume it's DC and then do all the analysis based on that. And there are some other papers out there that are trying to break down the input voltage waveform into several areas, like this area when it is close to zero, this area which is at its peak, and then this area when it is in the middle. Then kind of design 3 separate controllers and then pick the best one, basically, something like that. As it turns out, designing the controller is not that big a deal here because the output capacitor is very large, so your converter is sluggish to begin with. So it's not like my design would be better than yours because it actually improves the bandwidth, because we have already sacrificed the bandwidth because we wanted to minimize the ripple of the output voltage. Therefore, we have used a large capacitor to begin with. And it's a boost converter. Because of that right half plane 0, again, your bandwidth is again being sacrificed. So remember, power factor correctors are relatively sluggish. You cannot have a very fast transient response. You cannot expect to have a very fast transient response from a power factor corrector. And that's okay because your power factor corrector is on the front end, then you have other converters downstream, so those converters could be fast and provide a fast dynamic. Now, going back to this transfer function, I have plotted this transfer function, the Bode plot, for you guys to actually log. So the transfer function is 1 over 20, which was that sensing gain for the output voltage, then 200 over S. So S is the integration block, which is trying to eliminate the steady state error. And then I have a 0 and a pole. If you compare with the numbers that we used to use for zeros and poles, these numbers are way smaller. Like when we were working on a buck converter, your zeros and poles were like at 10,000 radians per second, large, at least larger than 5,000. Here you can see our 0 is at 60 radians per second and our pole is at 500 radians per second. You can see it's a very, very, very conservative controller. So if you plot this, because of this S term over here, if you look at very low frequency, it's actually coming straight down. So we are using this term 1 over S to eliminate the steady state error, make sure our output voltage is at 200 volts. And then I am hitting a 0 over here, then a pole over here, then it further goes down. If you look at the crossover frequency, it's only 10 radians per second. So it's a very, very conservative, a very sluggish controller. Why is that? Why do we make it so conservative? The reason is we would like to attenuate the 120 hertz ripple in the output of our controller. So here I'm looking at 120 hertz in terms of radians per second, which is 750. And actually looking at the magnitude of my compensation network at this particular frequency it is only 10% or 9%. So you can actually trying to attenuate the ripple, the 120 hertz ripple that exists in your output voltage compared to the output voltage of the composition network. So in terms of dBs, your attenuation is negative 20 dBs, which is actually quite good. So this is why you have a very small bandwidth, because you need to have good attenuation or a small number at 120 hertz. Then I have the phase diagram. The phase diagram doesn't give us much information because this is not the entire loop. This is just part of the loop gain. The other part of the loop gain is the control to output transfer function of our boost, which is I just talked about. It's really hard to obtain it because the operating point is moving too much. So we can mess around with this controller so you guys can see what happens. For instance, I am going to move. Okay, hold on. Let me do it theoretically first. So what if you come out and say, okay, instead of 60 radians per second, I use 6,000, and instead of 500, I use 5,000. You still get a good attenuation over here, but then your phase may get a little bit disturbed. Okay, and let's take a look at the results. Oh, come on. Or you can see that the system is having a hard time settling down. I probably should run it for a longer time. Your output voltage is getting close to 200, and you can see that the inductor current is just all over the place. But hopefully it's going to settle down. So it's not that big a deal. If you neglect this weird-looking transient, it's not that big a deal. You can play around with the zeros and poles of your composition network. The only thing that you have to make sure of is that your 120 hertz ripple is significantly attenuated. That's the most important thing. So let me go back and adjust it to what it was. Okay. All right. Another thing that I'm going to talk about is. Yes.
When we are increasing the poles and the zeros frequency, then the bandwidth should increase, right?
The bandwidth should, okay, just a little bit, okay.
And the response should be a bit faster than...
Well, ideally, yes, but there are so many other crazy stuff happening here that and we didn't drastically change it. We only changed it, like, we moved them 10 times to the right. So the bandwidth was still relatively small, even though before it was like 10 radians per second. Let me see how much it is now. It is still, I would say this term is the dominating term. It is actually still, so if you want to have a better bandwidth, you have to actually also increase this gain too. So now you can say, okay, my bandwidth was 10 radians per second, now it is 100 radians per second. Let's actually try that and see if we see a significant difference. Do we have good attenuation? Relatively good. Negative 13 dBs is still good. I don't know why I just keep switching to this. All right, so let's do that. Let's see what kind of a response we are going to get if I make this DC gain 10 times larger. And these guys are also shifted to the right. So this should be a slightly faster, but I don't think we will see a significant improvement. So you can see that actually the output voltage is regulated at 200, so that's good. Is it faster? I don't actually remember compared to the PV. It is not significantly faster. But what you can visually observe here is, even just by visually looking at this, I can see extra distortion in the inductor current. Or now, if I compare it with a very good-looking, oops, not this one. Where was that good-looking one? Yeah, it is this one. You can see that there's extra distortion in it. You know, here we have a dip. The peak is shifted to the left, and we have actually another dip over here, but here we are actually higher than where it is supposed to be. This is because of that, before we had extra, oops, I did it again. Before we had extra attenuation at 120 hertz. It was like only 9%, now it is 21%. So you can see that this ripple, if it gets to your controller, it messes up everything because it's being multiplied by everything else. So actually, there are papers working on this. There are suggesting solutions. Like one solution could be adding a notch filter at 120 hertz. So that notch filter kind of tries to eliminate or attenuates the 120 hertz component of the output voltage, but at the same time you can achieve a high bandwidth. So there are papers like that. And there are some control approaches like repetitive control and things like that that are, with some math techniques, you're trying to kind of filter out the 120 hertz ripple in this signal. Because as you can see, we don't want it because it disturbs the rest of the system. Okay, any other questions so far? Okay, so going back to the model. All right, let's move it back to a normal case. Okay, now what I'm going to do is I am going to apply a sudden change in the amplitude of the input voltage. So does it really happen in reality? So what I mean is my input voltage is, in a very exaggerated case, my rectified input voltage is, something like this. Then it, for instance, goes up a little bit. Okay? So remember, the output voltage should be 200 regardless, right? We have a loop that is controlling or regulating the output voltage. However, the problem happens is when you bring this signal over here. So this signal grows a little bit taller. And it is being multiplied by the output of the compensation, so the reference for the current gets a little bit taller. So that means you're asking the converter to send more current towards the load, and the load even doesn't need it because load hasn't changed, and the output voltage requirement has not changed. So the output voltage increases. And then this feedback controller recognizes that the output voltage was supposed to be here, but it's actually going up. So this signal goes down to compensate for this extra actually increase in the amplitude of the input voltage. So your output power is constant. When you increase, ideally, because your output power is constant, so this black one is the input current now. When your input voltage increases, your input current should actually decrease because the power should be constant. So let's see what big of a problem this is when I, in an exaggerated way, I jump from like a factor of 1 to a 10% extra input voltage, okay? Okay, actually, here it is. This is when the transition happens, okay? So all of a sudden, my input voltage had a higher amplitude. Therefore, the converter is not fast enough. So after the transition happens, my actually current increases. And then the system figures out, oh my God, the current should not increase. So finally, it settles down to a lower value. You can see that you're kind of tricking yourself. First, the current increases, the output voltage increases, then the controller realizes that, and then tries to correct itself. So you can see that here, if you zoom in, your input voltage is settled around 200, then temporarily goes up, then recovers back. Okay, this is because the output of this compensation network has to go down ultimately. So let's take a look at this. So remember, these two signals are the reference for your current. These two signals multiplied by each other is the reference for your current. Oops. So the input voltage increases. Ultimately, the reference for the DC value of the compensation network output should actually decrease. Now, to avoid this, because temporarily your output voltage is not regulated, goes beyond 200 and comes back, but to avoid this, there is a trick that they do, and we're going to talk about this trick. It's called a feed-forward constant power kind of a trick. I don't have a simulation for it, but here is the trick. So what they do is, let's go to a new date. Okay, so you have your power stage. And I'm just drawing this as a source, which is the output of my diode bridge, which is a rectified AC signal. So the trick is, well, similar to the previous case, we are still trying to regulate the output voltage. And we have a transfer function, which is our voltage compensation, basically transfer function. We get a signal that is relatively DC. And this is the extra block that we have to add. And I'll explain what X, Y, and Z are. K is just a sensing gain. So this signal is Y. And then ultimately we get IREF. And then this is our current mode controller. So we also need information about the inductor current. And then finally, it goes to the gate. Okay, so let's talk about these gains X, Y, and Z, these actually signals. We also need to add a peak detector. So this is called, the output of our peak detector is Z. So Z is the peak value of your input voltage, which is, before we label this to be VM, Vmax. And then I'll still need an X going in, and X is actually the input voltage. Okay, so as you can see, in order to avoid this situation that if the input voltage rises, the input current also rises, it should actually fall a little bit, we detect the peak value of the input voltage, And once we multiply x and y, we used to multiply x by y anyway. We just divide them by z squared, which is the peak value of the load. So you kind of have this feed-forward term that is trying to emulate a constant power load at the beginning before even the current actually goes high. Although implementing this thing in an analog controller might be challenging because you're multiplying two signals by each other and then you are dividing it by another signal, so it might be a little bit challenging, but there are lots of papers working on this, actually suggesting this. One last thing to talk about, the peak-on mode controller, and that is how did I get the value of the inductor, like 360 micro or whatever it was. Let's talk a little bit about that. So remember, our objective is to operate under continuous conduction mode. That means the average value of the inductor current should be larger than half of the ripple of the inductor current. Okay? So assuming that we are doing a good job in terms of the power factor correction, my source sees an impedance which is like a resistor, because ultimately we want the current to be proportional with the voltage. So it's like we are trying to emulate a resistance on the input side. So the average value of the input current or the inductor current would be the input voltage over the emulated resistance, RE. This should be larger than delta IL. Going back to the peak converter, in the first mode, only Vn is applied, so it's Vn over L times D times T. Vn dt, something like this. All right? So you get that D should be smaller than 2L over RET. And in a very, very simple approximation, neglecting the dynamics, you can argue that V out over Vn is almost 1 over 1 minus D over here. So D is 1 minus Vn over V out. And I just combine them together. Okay? So we get an expression like this. In this expression, we have the switching period, the output voltage, like 200 volts. The input voltage is variable, so we have to, keep that in mind. And then RE, which is the emulated resistance, is basically determining how much power we are consuming overall. So RE is easy to find out. So in the end, you end up with this, this expression. The worst case scenario would be something like this. So you can say that at light loads, we may actually lose power factor correction because we are going to go into basically CCM. We are going to go into DCM. It's not a very straightforward equation, so you have to look at the variations in Vn and then decide what the right value for your inductor should be. So in my case, 360 microfarads actually work quite well. Any questions? Yes?
Could you speak a bit about the emulated resistance? Like, where does it come into picture into a converter?
Oh, so the emulated resistance is, if you look at the input power, assuming that you are already doing the loop is closed, you're doing power factor correction, your power factor is almost 1, would be Vn RMS, In RMS. At the same time, it is V out over squared over R. Again, assuming that your output voltage is almost DC, neglect the ripple. Okay? So at the same time, we know that I RMS is okay. So we want our input voltage to be proportional with input current. So so the relationship, very simple relationship, is as if you have a resistance on the input side, basically. The whole converter is modeled by a resistor. So I is voltage over resistance. So once you plug that in, you end up with V in RMS squared over emulated resistance is V out squared over real resistance. So this gives you a relationship between the real load, the real resistance, and the emulated resistance. So we can actually calculate it. Any other questions? Okay. So this was all about if you're using the boost topology, and also the control approach that you have chosen is peak current mode control. Now you can also do average current mode control. Since in this class we have not talked much about average current control, we are not going to go into the details of that. Another very common approach for controlling the boost topology is the hysteresis control. So let's talk about a little bit about hysteresis control. So the topology is the same, boost. The objective is still the same, provide power factor correction or make sure your input current looks nice. But this time we are using a hysteresis. Control. Okay. Hysteresis control, or like bang control, the simplest example is when you want to, for instance, control the temperature of this room, you set the temperature, let's say, at 72 degrees. So actually what happens is you are defining a band, like if the temperature goes above 72 degrees plus 1, you turn the air conditioner on, let's say it's summertime, so to cool down the room. And if the temperature goes below 72 degrees minus 1, you turn the air conditioner off. So this is your set point, 72 degrees. Then you have a band. So the thermostat actually does this, has this band. You don't adjust the band. So let's say the band is 1 degrees. Okay? So if the room is too hot, let's say you are here, it's above where it is supposed to be, so you turn the air conditioner on, so the temperature comes down. Until you hit this point, then is now the room is too cold, okay, below, on the lower edge. So you turn it off, so the room gradually warms up because of the sun and everything. So you keep controlling yourself within these two limits, okay? So it's a hysteresis control or bang control, things like that. Now you can actually do the same thing with the inductor current, because remember, if you turn the switch on, the inductor current rises, kind of like when you turn the air conditioner off here, the temperature rises. And when you turn the switch off, the inductor current falls, kind of like here when you turn the AC on, the temperature falls. So it's actually quite simple. So let's say you have this reference for the inductor current. Okay, this is your reference for the inductor current, which comes from the multiplication of the output of the voltage compensation network by the input voltage, something proportional with the input voltage ultimately. And then you define these two bands. And you try to stay within these bands. Well, this is an exaggeration. The switching frequency is usually higher than this, and therefore the band is much narrower than this. This is just an exaggeration to be able to visually see it. Okay? There are advantages and disadvantages. For instance, you don't need the external ramp anymore. You don't have to worry about subharmonic oscillations anymore. You are still operating under continuous conduction mode, which is good. But at the same time, the switching frequency is variable now. We don't have a constant turn on, turn off kind of a mechanism. The switching frequency is determined by the parameters of the system, when it is that you get to this point, when it is that you get to this point, and then when it is that you get to this point. So that's, for instance, one period. So the major disadvantage over here is variable switching frequency. The other disadvantage is you are very sensitive to noise, okay? Meaning that your whole switching scheme depends on these points. If for some weird reason you miss these points, you actually lost the state, so for some reason you may actually run away. If you miss that particular point, okay, if there is some noise or some delay or something, you run away and then it's really hard to bring it back over there. So, I mean, there are methods of doing that, and there are a bunch of papers. One of them is wait for a particular time, and if you realize your switch hasn't been turned off, force the converter to turn the switch off. The other one is they actually define an extra band around, it's like the red line or whatever it is, and once you hit that red line, then you definitely have to turn the switch off or something like that. But anyway, these are the general problems associated with the hysteresis controller. Any questions? Okay. So this pretty much wraps up our discussion on power factor correction. It is still an active research area. Like, what about three-phase active power correction? There are several challenges in there. How is it that we can model the converter, coming up with the small signal model, things like that. Oh, one thing that I forgot to mention, one effect, if you're interested in modeling these, there are papers out there that are using generalized state space averaging to model these converters. The idea of generalized state space averaging is not only you consider the DC component of your signal, also you consider the fundamental harmonic of your signal. Okay, so for instance, your inductor current has a DC component, and then you consider the fundamental harmonic. You actually approximate this with some fundamental harmonic, and you consider both harmonics. So you have like two-dimensional kind of a model. So you have four transfer functions basically. There are lots of papers out there using this technique, especially for PFCs, because you have a significant 120 hertz ripple everywhere basically. So there are some papers out there. So interesting idea, interesting topic. We gotta do it anyway because we gotta make sure that the utility people are happy and we are actually complying with some of the standards in the country that you're trying to sell your product. The challenge is to make this converter cheaper and more efficient. By the way, we suggested boost topology, and boost topology usually works like for 200 watts, 500 watts, even 1 kilowatt. Boost converter works, but if your power is like, I don't know, 100 kilowatts, one single boost converter cannot do that. So that's another challenge, that use like an H-bridge that operates like a boost, or put a bunch of boost converters in parallel, those kind of things. But for instance, for a computer that you have, a desktop computer or a laptop computer, when you plug them in, the PFC is just as simple, could be as simple as a boost converter. One switch, one diode. There are other topologies that could be used for power factor correction. For instance, the flyback topology is also very popular because not only you can control, the harmonics of the current, it also provides isolation, galvanic isolation. So in some application, galvanic isolation is as important as power factor correction. So you would combine the two functionalities together and you use the flyback topology. I'm not really going to go into the details of the flyback topology. The principles of operation are very, very simple. Ultimately, you're trying to control the waveform of your input current. And there are lots of approaches other than the boost and the flyback, like for instance using the SEPIC converter or juke converter, and paralleling, putting two converters in parallel. So one common approach is, for instance, If you remember, we drew the input power with something like this. So this is the average value of the power, and then the fluctuation, the 120 hertz fluctuation in the power. So there are approaches, for instance, that there are two converters. One converter, for instance, processes this portion of the power. The other converter processes the other portion of the power and then just feeds it over here. So the other is more like an energy storage in addition to a converter, okay? So there are many, many papers and approaches out there. Like you kind of have two converters in parallel with each other, something like that. You can find at least thousands of papers on different ways of doing power factor corrections. So it's a very open area, and we just covered the bare minimum of it, basically. All right. Any questions? So we're going to move on to the last topic, hopefully the last topic of the class, which is soft switching techniques, okay? If you have had power electronics before, we kind of talked about soft switching techniques over there as well. I'm trying to use a different approach or maybe a different justification for why it is that we are doing what we are doing, and also hopefully we will have some time to introduce some more advanced approaches for soft switching. Okay, so let's talk about some background information. Why is it that we are interested in soft switching? Okay. Okay. When power electronic switches, semiconductor devices were, invented back in the 60s and 70s, the first switches that were invented were called SCRs, which is more like a I don't think we covered them in this class. In power electronics, we talk a little bit about them. They look like a diode with a triggering, basically, terminal. Or something like that. When they are off, they are blocking the voltage. When you trigger them, they conduct, and you cannot turn them off until they have to make their own decision. When the current goes back to zero, they turn off, basically. We don't care much about how they function, but the problem is, the major problem with SCRs was, if you look at the voltage of this device and the current of this device, if the variations of the voltage on the device when the device is off is so rapid, the device false triggers itself, so it turns on. Also, if the variations of the current that is passing through the device while the device is on is so quickly, you may actually have some localized heating within those, silicon, devices, and locally burn the device. So technically, your current. So if you have a particular surface for the current to flow through, when di over dt is so high, it is not evenly distributed in that surface. It's very localized. So the majority of the current goes through one point, and you basically burn that point, something like this. So one of the early motivations was to limit so the changes in the voltage or the changes in the current of the switching devices. This is especially for SCRs. Okay. So when it comes to SCRs, let me just write it down here. To avoid false triggering. Should be limited. Also, to protect the device, di over dt should be limited. This is specifically during turn on. Okay. So this was a major problem back in the 70s when these devices were relatively new. So they came up with some solutions, and gradually those solutions morphed into these soft switching techniques that we talk about these days, which is like zero voltage switching and zero current switching and those kind of approaches. So let's look at these. So for instance, you have this very simple buck topology. Okay, and you're monitoring the voltage of the switch as well as the current of the switch. And this is the current of your inductor. So this is happening during turn off, for instance. So let's assume that this is a relatively ideal switch. So when the switch was on, there was not a significant voltage drop on the switch. But when we turn it off, V in appears. Okay? So if you look at dV over dt, which is the derivative of this signal, it's like an impulse. Okay, it's a very sudden change, and it may potentially, do harm to your switch. Okay? So this is the ideal case. When switching transient is almost instant. So instantly the switch turns off, the voltage jumps up, therefore you have a significant di over dt. So what we are going to do on Thursday, further look into this and see how it is that we can actually add a snubber to your switch so to actually avoid significant or large dV over dt stresses. All right, so see you guys on Thursday.